Section P2 is going to be all about exponents. I know that you've seen all this before, all right? And some of it may be fresh in your mind, some of it may be a little bit fuzzy, so we're going to make sure that everybody's on the same page. There are several rules or properties about exponents that are useful to us so that they make solving things easier, make simplifying and combining like terms easier. So these are three of them. There's a couple more on the next slide. The first one is the product rule. So the product rule says that if I have the same base, notice the A's match, and they have exponents, whatever those exponents are, that I can actually add the exponents together like this. Okay? And the reason this works is because, for example, let's say we had 2 squared and we had 2 cubed. So if I had 2 times 2, that's 2 squared, and I had 2 times 2 cubed, that's 2 times 2 times 2. And how many 2's do I have? 5, right? There's 5 2's there, and the way that that happened is because you can take the 2 and the 3 as exponents and add them together. So it's just a quick example of it working for us in that way. So if, when we're multiplying them here in the product rule, we end up adding the exponents, what do you suppose happens when we divide them? Yeah, we subtract. So on this one, we end up with a to the m minus n. And kind of, again, an example of seeing that work, I'll just still use my base of 2. So if I had 2 to the 4th here over 2 to the 1st, well, 2 to the 4th means I have 2 times 2 times 2 times 2. And 2 to the 1st means I just have one of the 2's. And as they reduce, I end up with 2 to the 3rd when I'm done. And of course, again, you can see that I'm getting the 3 by taking 4 minus 1. Okay, so subtracting those exponents. There are a few that are sort of in the category of power rules. The first one kind of feels like distribution. It's not, because distribution is multiplication distributing through addition or subtraction, but it does have that same feel to it. On this one, when I have a power raised to another power, I simply multiply the powers together, m times n. And as an example, if I had 2 squared cubed, 2 squared means I have 2 times 2, and that being cubed means I do it 3 times. Okay, I ran out of space. Let me make it a little bit smaller. And again, how many 2's are there then? There's 6. And where do I get the 6? Well, I'm multiplying the 3 and the 2 as the exponents. Okay. The next two, again, also have that sort of a distribution kind of feel to it. A b to the m is actually a to the m, b to the m. And likewise, a over b to the m is a to the m over b to the m. And if you want to do, we can still use the a and the b if you'd like, and we'll just make the m a 3. So if I had ab to the 3rd, you can see how I would do ab, ab, ab. Right, that's what it means to the power 3. And then I can rearrange because I have the ability to do commutativity. We talked about that last time. So I can switch the order, right? 5 times 2 is 2 times 5. So I shift all the orders around. I collect all my A's together, and then all my B's together. And of course, you see that this is A cubed, B cubed. And I won't show the second one on there, but it works the same way. Yes, ma'am?
In order of operations, if it was like AB raised to the n, would you multiply A and B first? So
If you knew the values for A and B, you could. Yeah, you definitely could. It actually will work either way. But if you know the values for it, yes, it would be simpler to multiply the A and the B values together first. You evaluate that part of it and then raise it to whatever power's there. Yeah, good question. Okay, there's 2 more properties that we want to discuss. It's what happens when we have negative exponents and 0 exponents. So negative exponents can be rewritten in a positive form by moving them. So if they're in the numerator, they move to the denominator, like this. If the negative exponent were in the denominator, we would move it up to the numerator and it would make it positive. Okay, so it's a reciprocal maybe another word that you've heard, or a flip of a fraction. So anytime you have a negative exponent, that's what happens. And you can see the note on here, and it's really important to write that down. In general, we will always have our answers written without negative exponents. Most of the time, directions will tell you that as a reminder, but simplest form indicates that we would do it anyway. Okay, so positive exponents. Does anybody remember what a to the power 0 or anything to the power 0 is? 1. You're right, it is. And I'd kind of like to show you why, because it's a fun little trick. It is the number 1. So let me actually start with something that you're familiar with from the previous slide. Let's say that we had a to the n over a to the n. What is that? It's 1, right? You divided it by itself. So this is very easily the value 1. I've got the value divided by itself. But on the previous slide, I told you that when you had a quotient like this with these powers, that you could subtract the powers, yeah? Yeah, what's n minus n? It's 0. So there are two different ways of rewriting that a to the n over a to the n. One of them is the value 1, which I wrote at the beginning, and the other one is with subtraction of exponents, which becomes an exponent of 0. So they are, in fact, equal to one another. And that works for anything as long as the base itself is not 0. So the one thing we can't have, and we won't talk about, by the way, as well, is 0 to the 0. This doesn't make any sense, okay? But anything else as a base number, positives, negatives, exponents, or not exponents, fractions, decimals, any of that to the power of 0 is going to be 1. So what we're going to do next is we're going to do some examples, and the whole goal of doing these is to use those properties, 1 through 5, that we did, to simplify what's there. Now, in particular, if we're dealing with numbers, like we are on number 1 and number 2, we're going to multiply them out, okay? And then if we're dealing with variables, we can't, so we're just going to write them in the simplest form we can, which will be in an exponential form. So on the first one, what you see is you see negative 5 to the negative 3. Now, we talked about this kind of a perspective or like view when we talked about this last time, but I know not all of you have probably gone and actually done any of these problems. What I want you to remember is that this is actually telling you that the 5 is raised to the power negative 3, not negative 5. Do you remember we were talking about that last time? If it were supposed to be that the negative 5 was raised to the power, the negative 5 would be in parentheses, and it isn't. So if it helps you to sort of drop them in as to where they really are, this is really what's going on. I'm doing the exponent part first, and that negative at the beginning is kind of like having a negative 1 multiplied by it. Order of operations. That's what we really see happening here is order of operations. You just have to be careful about which piece of it is being raised to a power. So I do have this negative in front. And then property number 4 told me that when I have negative exponents, how do I change them into positives? Yeah, I put the reciprocal. I move them down to the denominator. So the numerator becomes a 1, and then the denominator becomes 5 to the 3. Does anybody know what 5 cubed is? Yeah, it is. It's 125. So I have the negative still at the beginning, and now I have 125 in the denominator. Is that okay? All right. So with that same idea, how would I rewrite on number 2 the 6 to the negative 1? Yeah, it's 1 over 6. Or you could write 1 over 6 to the 1, right? But it's 1 over 6. What is 5 to the 0? It's 1, right? We did that as property number 5. It's 1. So we need to combine 1/6 and 1. There's 2 different answers that you could come up with that are both equally right. Decimals are not equally right here because they'll be repeating decimals, so we're not interested in that. Did you have an idea?
Oh, for that.
Mm-hmm.
Either 1 and 1/6, or if you go 7 over 6.
You're right. All right, so 1 and 1/6 is a mixed number. We're just combining the 2 pieces together. So think about what would happen if you were measuring something. You measured 1 foot and then you measured 1/6 of a foot. Well, it's 1 and 1/6 long. If you wanted to do it in a fraction that's improper form, you can get common denominators. And just as a reminder, because we will be asked to do that some of the time to work with them, 1 and 1/6 means I have 6 over 6 plus 1 over 6. And that's what the 1 means, is 6 over 6. And that's why it becomes 7 over 6. So unless it's indicating to you how they want your answer, either answer is acceptable. Right? One's not better than the other. All right, let's do one with some variables in it now. All right, so the first thing to recognize on number 3 is while I do have parentheses, there's nothing within each of the sets of parentheses that combines or simplifies, right? So take a look at the first one. I have the number at the beginning, the coefficient, the -6. There's no other coefficients. I have one that has a base of A, but there's nothing else that has a base of A. And I have one of them that has a base of B, and there's nothing else that has a base of B. So within this set of parentheses, there's no simplification that can be done within. And the same is true for the second one. So everybody see that okay? So what that really means is the parentheses are rather irrelevant. They're just indicating that there's multiplication going on. So I can sort of lift the parentheses away and everything is being multiplied. It's all just a big giant multiplication problem. So since that's the case, we're going to use our property that says that we can commute values, right? We can shift them around, and we're going to collect the pieces that go together. So in other words, I have -6 times the 3. Those pieces are the coefficients, and they'll go together. And if you don't want to write out -6 times 3 and you just want to write down -18, it's fine. I just want to make sure you see that I am paying attention to all the pieces. There's 2 pieces that have a's in them. I have an a to the 7th and I have an a cubed. So those are going to be combined together because they have the same base. And then I have b to the 4th and I have b to the 5th, also having the base of b in common. So this is sort of an intermediate step. You don't necessarily need to show this particular step I just did if you can see the pieces aside. What is -6 times 3? -18. All right, the other 2 pieces actually use the properties that we were discussing before. So what is a to the 7th times a cubed? Yeah, a to the 10th. I add the exponents. That was property number 1. And b to the 4th and b to the 5th would be b to the 9th, also adding the exponents. So we end up with -18. Wow, that wasn't very good. A to the 10th, b to the 9th. All right, few more. Same directions to simplify. Yes, they're getting messier as they go. It's the way it works, right? Start with something that's pretty straightforward and get a little bit more complicated. On this one, you'll notice there are some exponents that are negative, but not all of them. You'll notice I have negatives in front of values as well, like coefficient negatives. So there's a lot going on in this problem. Agreed? And there's also more than one way to do this problem and get the correct answer. So one way would be to deal with the fact that there's a lot of negative exponents, and I don't like negative exponents. I want to make them positive. So you could fix the negatives into positives to start. You could do that. Another thing you could do is you could see, oh, look, there's a P on top and there's a P on bottom. There's a Q on top and there's a Q on bottom. And I could use the property number 3 that says, oh, I can do the number 2 that says I could subtract exponents because they have one on top and one on bottom. So any of that's fine. I think, I'll let you guys decide. What do you want to do? Do you want to get rid of negative exponents, or do you just want to combine all the exponents at the get-go with subtractions? What? Nobody's going to talk to me today.
Combine them all.
Combine them all. All right, we will do that. So if we're going to combine them all, one thing we can recognize at the get-go here is that these 2 negatives are going to cancel, right? Because it's really just a -1 multiplied in each of those cases. So I don't really need these 2 negatives. The 3 has to stay on bottom, so leave the 3 where it is because it doesn't have any exponents, okay? So in terms of coefficients, I still have a 1 on top and a 3 on bottom. And then let's deal with the p's. So on the top right now, it says p to the -1. Actually, let me just write it out to the side like I was going to. And then on the bottom, this just says p. What's the exponent on the p that's on bottom? It's a 1, right? It's not there, so it's an understood 1. There's a 1 right here. So as I'm doing my subtraction, I need to subtract the 1 that is the exponent of p on the bottom. And then I can do the same thing with q. The q on top has a -1 exponent, And then I need to subtract the exponent that's on bottom, and the exponent that's on bottom is actually -3. Okay, it's easy to lose a subtraction sign or a negative sign when you're doing this because you're subtracting the negative, right? And it's very easy to think, I already put the negative in there. So make sure you keep all the negatives that are supposed to be there. All right, so I still have my 1/3. What is the exponent for the p here? -1 minus 1. -2. And then on q, I have a minus a negative, so I actually have -1 plus 3, which gives me what? Yeah, it's q to the 2. So it's real tempting to think that we found our answer. But back over here, I made a comment in the middle of the page, and I said it's really important. In general, our answers need to have positive exponents when we're done. And so one of these isn't. In particular, the p's exponent is not positive, right? So we're going to take one step to rewrite. The q has a power of 2, which is positive, so it will stay on top. You can write a 1 in front of it if you want, but it's not necessary. We still had a 3 on bottom anyway. And then the p has to move down to the bottom and become p squared. Because it was a -2, and now it will be a +2 in the denominator. Okay? Let me show you on this one, if you change the exponents locations, how it looks instead. So write it down if you want, or don't. It doesn't matter. I'm going to make this a little bit smaller so I have some more space over to the side. If you decide that you want to do shifting of exponents, the negatives will still cancel out. So you'll still end up with, it'll really start with p to the, what do I have, -1, q to the -1 over 3, p q to the -3. Looks like that. So if I move things around, right, instead of just subtracting exponents like we did on ours, we would end up moving this p down. So the numbers always stay. 3 stays, and now I have the p squared moved down. The q to the -1, that q also would move down. So this would be q to the 1. The p that's already here would stay. So I would have p. And then, oh, I'm sorry, when I moved it, I made it a -2. Made it 2, I'm sorry, I didn't mean to do that. P to the 1. Okay. And then the q also gets moved. This q to the -3 gets moved. So I have q cubed up here. So I would end up with q cubed over 3. The p's would combine, so I'd have my p squared and a q. And then the last thing to do would be to recognize that the q to the 3rd and the q here, one of those q's cancels out. Or you could do it with subtraction of exponents. And so you'd end up with a q squared on top and a 3p squared on bottom, just like the other way that we did it. Okay? So it's just a preference thing on whether you want to deal with the negatives. I feel like the first way we did it, we dealt with a lot of negatives, a lot of subtraction with negatives. The second way, we moved a lot of things around. And so there's a shifting process where we could lose some things. So either way has sort of some inherent places where we can make mistakes, right? They do. All right, number 5. How does number 5 look different than, say, number 4? What do you notice that's different about 5? Okay, we've got an exponent raised to an exponent. We haven't done one of those yet. That's true. There's something else, too. What's that? There's some parentheses. We didn't have any parentheses on the last one. Also true.
The exponents are like equations.
The exponents look like they're a formula, right? They've got addition and subtraction in them. They're not just a simple number. Yeah, and so there's something inherently different about that because I've got addition and subtraction in my exponents as well. It works the same way. It just makes it a little bit messier is what it really does. It just makes it messier. Now, there is something that's really good about this, though. Do you notice that I only have one base and they match? That didn't happen on the problem before, right? I had bases of q's and I had bases of p's, and so I had to deal with them separately. I don't have to deal with these separately because they both have a base of x. They match, which means that all the properties that I had where the bases have to match, which is practically all my properties, are going to apply. I'll be able to have a single term at the end with x as the base, and x will have an exponent, and that's all I'll have, okay? So there's several things that we could do. What do you see that you would like to try first? I've got lots of options, so I'm not gonna show you multiple ways, but what do you see as an option of something we could do here?
Move the bottom x up to the top and then combine by terms.
Okay, so we could actually, instead of moving it, how about we do subtraction? Is that okay? All right, so we could combine the part that's inside the parentheses, which is actually a pretty good place to start because we have the ability to do that, right? Inside the parentheses, it can be simplified. So the value that I currently have is x to the 2a minus 3, and then I would subtract the exponents in the denominator, the exponent from the denominator, so negative 4a plus 1. Okay? And they are expressions now. It's not just a simple number. So I have 2a minus 3, and then minus this negative 4a, so it's plus 4a, and minus 1. So I'll just write those above just to make sure that we see that well. So this is actually plus 4a and minus 1 when I distribute the negative through. Is that all right? Just a reminder for us. So I have x. So now I have this 2a and this 4a, so that gives me 6a. And then I have this negative 3 and this negative 1, which gives me negative 4. And all of this is raised to the power negative 4. It actually looks a whole lot better than it did before already, doesn't it? It really does, without the fraction in there. Again, I have a couple of different options. What would you like to do next?
Just put the 4 on the bottom.
Yeah, so it's kind of tricky. Part of my exponent is positive, the 6a, or at least potentially so, right? And the other part of the exponent is negative because it's a negative 4. So we don't want to deal with them separately. We still want it to be combined. So we don't want to separate them like what you're describing. Multiplication might be a good choice. One of our properties said that I have a power to a power, which I do have here. I can multiply the powers together. So that's a good option. So I could take this, and I have my x, and then I can multiply 6a minus 4 times the negative 4, right? Multiplication of the exponents. So my x gives me negative 24a, and then plus 16. So I told you before that we don't want to have negative exponents, and the problem is that depending on what a is, this might or might not be negative. What if a is negative 1? It'd be positive, wouldn't it? 24 plus 16, I'd have a power of 40. So there's no way of knowing is this exponent positive or negative, which means I get to stop. That's what it really means. I don't have to keep going and trying to guess because I have choices on what could be happening here. So this is a perfectly viable place for us to stop. We wouldn't want to separate things out. The other thing that, I should have keep this so I can try and figure out sometimes, Ben might have been suggesting, I was thinking about what you were suggesting, is you might have been suggesting that I take everything and put it on the bottom to the power of 4.
Yeah.
Is that what you're meaning?
Yeah.
Okay. And you could do that too. So if you think of it that way, you would have 1 over, and then you'd have your, oops, that was not a 6, x to the 6a minus 4 to the power 4 like this. And you distribute it through. It will be the same thing. The signs will just be different. So you would end up with an answer that looks like, so another version of this, 1 over, and it would be x to the 24a minus 16, which would be another perfectly reasonable way to leave the problem. Because again, I don't know if that exponent's positive or negative right now, so leaving it in the denominator there would be perfectly fine as to leaving it in the numerator. The only thing that might happen in my math lab is it might actually say to have the answer written as x to a power,
Yeah.
in which case you'd have to shift it at the end either way. So that's a possibility just on form. Okay, I think I have one more of this variety. Yeah. This kind of combines the last two problems together. So like Wesley mentioned, I've got the parentheses, like I did in the last problem. Somebody else had mentioned that I have powers to powers, which I did on the last problem. But like on problem number 4, I have multiple bases. I have x's and y's. Okay, so I'd like to pause for a moment and give you a chance to try working this problem through on your own. And once you've completed it, check with a neighbor, see if you have the same answer. So you don't necessarily have to do it the same way. Whatever process you choose has potential for being okay. Right? There's things we can do that are wrong, obviously, but there's plenty of things here that we can start with that are also right. So give it a try, and we'll see if we can get to the same answer among us. Okay, out of curiosity, how many of you started by working with the inside and trying to make it cleaned up first? I think that might be the easiest way on this one. Certainly not the only option, but your numbers will probably stay smaller for longer, which is often helpful. There's also some interesting coefficient things going on this problem that we didn't have on the problems before. For example, the 15 and then 18, those have a common factor, right? We haven't done that here with me here yet anyway. What do 15 and 18 both divide by? 3, and it'd be really nice to make those smaller as 5 and we have 6, 5 and 6 before I start, right? So So let's actually take a look at simplifying the inside as we can first. So the first thing I would like to do is make those numbers smaller by dividing them both by 3. We have the same kind of issue with exponents that I had on a couple problems back, where I can either shift them around or I can do subtraction. I think let me shift them around this time, since we did the subtraction as the first sort of way we did it before. So I have the negative, I have the 5 on top, I have a 6 on bottom. And then I already have an x squared and a y to the 8th that will stay put. And I have a y to the 9th that will stay put. And then my x to the negative 2 will come down as x to the 2 in the denominator. Is that okay so far? All right. So taking a look at my y's that are left, there's y to the 9th here, and there's y to the 8th here. 9 minus 8 is 1, so this is going to leave me with a single y on top. And then in the bottom, I have x squared and x squared giving me x to the 4th. So it already feels a lot better with single variables instead of multiple variables that are matching. There's a negative 2. So the fact that it's negative could flip the fraction and become positive. So I'm going to write it that way next. So now I have it still the negative at the beginning, 6x to the 4th over 5y. But now it's to the positive 2 because I flipped the fraction to get rid of the negative exponent. And then just as a reminder, what this really means is that I have negative 6x to the 4th over 5y times negative 6x to the 4th over 5y. So this is just sort of a reminder. So as we're thinking about simplifying from here, notice that when I square the negative, it becomes a positive, right? Because I've got a negative times a negative, so this will become positive. I also have to square the 6, right? 6 times 6, so I have 36. I have x to the 4th squared. That would be x to the 8th. Okay, and then I have to square the 5, right? 5 times 5, so that's my 25. And then I have the y squared. So not the only way of doing the problem, but it kind of like cleaning things up before I make them bigger and messier, and then consolidating at the end. So one way of doing that. Okay, the last thing that we're going to talk about in this section of material is scientific notation. I'm hoping we'll at least finish that part of it today, and then we'll start up with P3 next time. So scientific notation. Scientific notation has a specific form. It looks like a number a times 10 to the power n, and there are some conditions. The value for a is between 1, the absolute value is between 1 and 10. So it can be positive or negative, it doesn't matter, but the numerical value is between 1 and 10. And the value of n is that it's an integer. So n can't be a fraction or a decimal or something like that. It can be positive or negative, but we're looking at positive and negative whole numbers.
Could it be 10?
It couldn't be 10. It can be 1. So we don't need it to be able to be 1 and 10, so we allow it to be 1. That's the standard way of doing it. Most of the time it's not going to matter. But yeah, we don't let it be equal to 10, but we can let it be equal to 1. All right, so here's what I want you to keep in mind, okay? There's two different sort of thinking on how to talk about scientific notation. One talks about those negative and positive exponents as moving things right and left. You've probably heard it that way before. That's how I was taught it. And the problem is that depending on whether you're moving into scientific notation or moving out of scientific notation, you have to switch. Am I moving right or am I moving left? So instead, what I think makes it easier is to remember the following. That a negative exponent is a small number. That's a number sign, by the way. It's not a hashtag. And a positive exponent is actually a large number. And what do I mean by small and large? Well, I mean smaller than 1 and larger than 10. That's all I mean. So a small number is something smaller than 1, and a large number is something larger than 10. So if you see this one right here, this 5 here tells you, because it's positive, that what kind of number do I have? A large number, right? I'm going to have a large number. The 5 also tells you how many places to move the decimal point for it to become, in this case, a large number. So I'm going to move the decimal 5 places, and I'm going to make it larger. So the number is going to be, instead of being 5.98, it's going to be bigger than 5.98. So we're going to get 5. I'm going to write out what it's already at and put some zeros on the end so we'll be able to see them moving. And we're going to move it 5 times. So here's 1, 2, 3, 4, and 5. So right there is my number that I'm going to have, 598,000. The number is 598,000. And I would contend that that's a large number. If I offered you that much money, you'd take it, wouldn't you? I would, absolutely. Now on number 8, the negative exponent indicates that it's going to be a small number. So it needs to get smaller than it currently is. And it needs to do it by moving it 2 decimal places. So here's my 5.98, and it needs to become smaller. So the decimal places have to move 2 to the left in this case. I have a 0.0598. It became smaller. Now, if we're moving the other direction from standard numbers into scientific numbers, we need to place our decimal point so that we get a number between 1 and 10. So here's my number, 16 million and some change. In order to have a number between 1 and 10, the decimal point has to be between the numbers 1 and 6. Okay? So as I'm doing this problem, my answer has to be 1.6. All the numbers stay except the zeros aren't necessary at the end. So 587. And it will be times 10 to a power. I mean, like, that's what it's going to be. The question is, what's the power? Well, first of all, let's decide, is it positive or negative? Well, what kind of number did we start with? A large number. So is the number going to be positive or negative? Positive, because positive exponents mean I have large numbers. So I've got a positive number. The next question is, how many places did I move the decimal? Well, you don't see a decimal point in this problem, but that means that it's after the last 0, right? So I moved it 3, 6, 7 places. So this is to the power 7. On this one down here, the decimal point would have to be located between the 9 and the 8. Like that. And again, is it a positive exponent or a negative exponent? It's negative because it's a small number that I'm starting with, right? Absolutely. And the question is, how many decimals do I move it? So here's 1, 2, 3, 4, 5, 6. This one's also 7, but now it will be 10 to the negative 7th. The last problem, I promise, is super fast. We're going to do it piecewise. Whoa, whoa, whoa. I meant to do that. What is 9.3 divided by 3.1? It's 3. And then we can use our properties of exponents. These are the bases, right, are the same. They're bases of 10 with powers. And I would simply subtract my exponents. So this is times 10. And it would be to the 12 minus negative 5. And what is 12 minus negative 5? 17. So again, it's like pieces. The coefficients in front are alike. The values at the end are alike. And when I'm done, I need to make sure, is it in scientific notation? Is 3 times 10 to the 17th scientific notation? It is. It has the right form to it, so we're good to go. All right, so homework due on Friday before class. 9 a.m. is the cutoff time. Sections P.1 and P.2. See you guys on Friday.